Okay, I'm going to pick up where I left off last time. I showed the spreadsheet, which shows that as the frequency goes up, the average optical power of a modulated light wave goes down as the frequency increases. Okay, and so what we're going to do is we're going to define the 3 dB bandwidth, f3 dB, as the frequency at which that output is half of the input. And so we're going to define this so that P prime naught of f at f 3 dB, sorry, f, so this is evaluated at f 3 dB, P naught prime evaluated at f 3 dB is equal to 1/2 P naught. Okay, so that's how it's defined, and we call this the 3 dB bandwidth. We could call it a 3 dB frequency, but it's typically called a 3 dB bandwidth. And in our fiber optic systems, what we're going to see is typically that this 3 dB bandwidth is, to a good approximation, just related to the pulse spreading in exactly the same way that the maximum data rate is related to the pulse spreading. That is 1/2 delta tau, where delta tau is our pulse spreading. That is exactly the relationship we used here when we said that, okay, with pulse spreading, we want the pulse spreading to be less than half of a bit period, and that gave us a maximum data rate of 1/2 tau. And so the frequency and the data rate have the same units, and so essentially, and so this works out, and this is a familiar relationship. So this 3 dB bandwidth and our maximum data rate are two ways of characterizing our fiber optic system. Let me show you the typical behavior of this decreasing function of f. How does this behave? Well, typically, typical system behavior is as follows. It's a Gaussian frequency response. So we have a Gaussian frequency response, and I'm going to write that P naught prime as a function of f over P naught is equal to e to the minus alpha f squared, where alpha is some constant. So this captures the frequency dependence as a Gaussian form. And what we're going to do is we're going to rewrite this as e to the minus, instead of the constant alpha, I'm going to write log 2, natural log of 2 f over f 3 dB quantity squared. And so my constant is the natural log of 2 divided by f 3 dB squared. And so now this form, this is a Gaussian form in f, and this form gives us then that the P naught prime evaluated at f 3 dB divided by P naught really is 1/2. Okay, so this works out. You can verify that. What I'll do is I'll show you that how this equation looks. It is a Gaussian, and if I plot P prime over P, P naught prime over P naught, it's going to start at 1, and it's going to go down to 0 as a function of f, and so at very high frequencies I get 0 response out of the thing. And so this is a Gaussian curve here. I also like to deal with ratios in decibel units, and so what I'm going to do is I'm going to make another plot, P naught prime over P naught, in dB units, and that's going to start at 0, and it's going to go down from there in a parabolic shape like this. So this will be a parabola. That's because the Gaussian has an f squared in it. So this f squared then becomes the square in the parabola. Okay, so this is what that loss, frequency dependent loss, looks like in both linear and decibel units. What I'm going to do now is I'm going to write the system loss as two pieces. One piece that applies to even DC, and another one which is frequency dependent. So in our optical fiber, for example, our total system loss and this is going to be in decibel units, is going to be the sum of the DC loss, L naught, plus the frequency dependent part as a function of f. So this is a fixed loss, essentially the attenuation of the fiber, and this is going to be the frequency dependent loss part that characterizes the frequency dependence and characterizes essentially that effect on the optical power output as a function of the modulation frequency. And we saw that in that spreadsheet. So what we'll do is we'll use a positive loss convention, that these are all zeros, greater than 0, and therefore we can write that this frequency dependent loss part in dB units as a function of f is, and now we're going to use our sign convention, minus 10 log 10 of P naught prime as a function of f over P naught. Okay, so I've taken this ratio P naught prime over P and I've converted it into a decibel, positive decibel loss using this equation here. And now what I'm going to do is I'm going to show you how that all, now I'm going to plug in that Gaussian model. Now I'm going to go and plug in this Gaussian model for the loss into this decibel version of this equation. What I'm going to do is I'm going to note first that off to the side that the log base A of x is equal to the log based B of x all over the log based B of A. And I'm going to use that in this derivation here. And I'm going to start with LF in dB units as a function of f as minus 10 log 10. And now I'm going to plug in this Gaussian model, e to the minus log 2 of f over f 3 dB, quantity squared. Okay, and now I've got the log base 10 of e raised to a power, and I can use this log conversion thing, and what I'm going to get is minus 10 natural log of e to the minus ln 2 ratio squared divided by the natural log of 10. And so finally this comes out to be 10 ln 2 over ln 10 of f over f 3 dB, quantity squared. Finally this is 3.01 f over f 3 dB, quantity squared. So this is the result I'm after, and we note that this loss this decibel loss, frequency dependent part of it, evaluated at f3 dB, really is 3 dB, 3.01 dB. Okay? So what I've done here is I've taken the Gaussian model for the frequency dependent loss part, and I've calculated it, and I've calculated at any frequency in terms of the 3 dB bandwidth. Okay, I'll stop here. Thanks.